Hey Yarpan, have you ever wondered how complex signals can be analyzed and simplified into frequencies?
Absolutely, Sahan. It's fascinating how the Fourier series and the discrete Fourier transform, or the DFT, play crucial roles in this. Let's dive into these concepts and see how they're applied in real world scenarios. Let's take a moment to understand how we actually calculate the Fourier series. Imagine you have a wave and you want to find out what frequencies make up this wave. The Fourier series allows us to do just that. At its core, the Fourier series compares the original wave to sine and cosine waves of various frequencies. It calculates values which tell how much of each frequency exists in the original wave. This is a bit like finding out which ingredient went into making a complex dish. To find a specific value, we multiply the original signal by a sine or cosine wave, the same frequency we're interested in. Then we sum up these products over the signal's entire period. In other words, we find the total area of the product wave.
Exactly, Arpan. Moving from continuous to discrete signals, which are more common in digital systems, we encounter the discrete Fourier transform or DFT. The DFT translates a sequence of discrete signal values into components of different frequencies. This is crucial because in the digital world, we work with sampled data. Here's a simplified way to think about DFT. We are still comparing our signal to sine and cosine waves. But since our signal is made from discrete points, we only look at specific intervals. Also, the number of sine waves is equal to the number of samples in our signal. The frequencies of these sine waves are integer multiples of the frequency whose period is equal to our signal duration, which is called the fundamental frequency. For instance, consider a simple signal consisting of 8 samples. That means we have 8 frequency bins starting from 0 up to 7 times the fundamental frequency. Let's take the sine and cosine of fundamental frequency. We multiply each sample point in our signal with the sine wave and with the cosine wave, and then we add them up separately. Repeat this process for other 7 frequencies. Voila! Here we have the DFT for our signal.
This is a simplified example, but it illustrates the power of DFT in identifying the frequency components of a digital signal. However, as you can see, to compute the DFT, we need to multiply 8 samples with 8 different frequency waves. Overall, this algorithm has time complexity of order n squared. In addressing this computational challenge, the divide and conquer strategy offers a groundbreaking solution.
Do you know? Divide and conquer is not just a strategy, it's a philosophy in algorithm design. It involves breaking a problem down into smaller, more manageable pieces, solving each piece independently, and then combining those solutions to solve the original big problem.
It's like solving a jigsaw puzzle. You divide the puzzle into sections, work on each section individually, and then piece them together to complete the puzzle. This approach is efficient and can significantly reduce the complexity and time needed to solve the problem. In computational terms, divide and conquer algorithms are designed to minimize redundant calculations and exploit the inherent structure of a problem. This is done by recursively dividing the problem until it reaches a base case that is trivial to solve.
The beauty of this method lies in its simplicity and power. It's used in many well-known algorithms such as word sort and quicksort, which are much more efficient than their straightforward counterparts. However, let's talk about its application with the discrete Fourier transform.
When applying the divide and conquer approach to the DFT, we arrive at the FFT or the fast Fourier transform. The genius of the FFT algorithm is in how it reduces the number of computations needed for the DFT from order n squared to order n log n, where n is the number of samples. This efficiency is achieved by exploiting the symmetry and periodicity properties of the discrete Fourier transform. The FFT algorithm begins by dividing the DFT computations of a sequence of endpoints into two separate computations of n by 2 points, which in our case is even and a odd. This division is performed recursively until reaching base cases, typically when the sequence of length is a power of 2. The key insight is that for many common signals and functions, the DFT exhibits symmetry and periodicity properties. The FFT takes advantage of this by combining the results of the smaller DFT computations in a way that avoids redundant calculations.
Let's illustrate with a simple example. Imagine we have a signal made up of 8 samples. Each of those data points must be multiplied by the 8 different frequency waves. Here, we are only illustrating cosine for simplicity. That means we need 64 complex multiplications. But due to the periodic nature of sinusoids, these waves of different frequencies overlap in a predictable way. So, we can see sort of duplications at some data points. Therefore, instead of performing 64 complex multiplications, we need only 24. But how do we know which calculations are redundant?
Well, we split our 8 samples into even and odd index points. Then in the even index points, we can see that at the location of the samples, the value of the first 4 waves and the waves of their corresponding second 4 waves are the same. A similar pattern can be observed for the odd index points, except the values of one wave are the negative of the other. That means we don't have to do all the multiplications for the second half of the frequencies. Once we read an even sums for the first half of the frequencies, we can reuse these values to find the upper half.
So, we cut the required number of calculations in half. To achieve the order of n log n complexity, we repeat the same trick. Split the samples again and again into even and odd points until we are down to single data points.
This process leverages the fact that the DFT of a sequence can be expressed in terms of smaller DFTs. It's a brilliant use of the divide and conquer strategy, allowing for faster computation, especially for large data sets. And it's not just about speed. By reducing computational complexity, FFT enables real-time processing of signals and images. Crucial for applications that require instant analysis and feedback, like live audio processing or real time medical imaging. Moreover, the FFT's efficiency opens up possibilities for complex analysis and algorithms that were previously thought to be too computationally intensive. From enhancing signal clarity to extracting detailed information from large data sets, FFT has become a cornerstone of modern digital signal processing.
Consider its application in electronics, like in digital filters and spectrum analyzers. FFT allows for the efficient analysis of electrical signals, identifying noise frequencies and filter them out. Or in designing more efficient communication systems, where understanding the frequency components of signals is key to minimizing interference and optimizing data transmission.
In image processing, the FFT is indispensable. It's used for image filtering, compression, and enhancement. By transforming an image into the frequency domain, we can isolate and manipulate specific frequency components. For example, look, here we see the FFT applied to compress the image of a boat. Next up, we use the FFT to sharpen that image. The divide and conquer approach, especially through FFT, revolutionizes how we process digital signal and images by making tasks that were computationally very intensive to tasks that are feasible and efficient.
Absolutely, Arpan. The implications for technology and science are profound. It's a perfect example of how advanced algorithms can unlock new possibilities in engineering and beyond.
Look, we've just scratched the surface today, but I hope this conversation sparks an interest in exploring these algorithms further.
Thanks for joining us on this deep dive into fast Fourier transform. Until next time, keep exploring and asking questions.